All right, physics dorks, it's time to watch another video on charge. I'm just going to do a little bit here on charge and capacitance. Now remember, the whole idea is hopefully you got done with that worksheet on lightning or the little video, and you're moving electrons. Okay, and what they came up with a long time ago is the idea that it's 1 coulomb, it's a measurement of charge, is what we've been talking about. It's that many 6.25 times 10 to the 18th electrons. So that is a measurement of coulombs. Electrons don't have much for charge, but so it takes a lot of them to make up 1 coulomb. And what'll happen is that when these charges are in certain locations, I just lost my pen here that I was using to mark with. 1 second, freaks. Hold on. Where? Dang it. Okay, here we go. I'll use this. All right, so anyway, you get a charge right here. And what can happen is that from this charge, you'll give off these electric field lines. And it's no different than around like a magnet. They give off magnetic field lines. These field lines, they exist out there emanating from either a positive or negative charge. And so you get these fields that, well, why this is kind of a big deal is because if you put one charge of the opposite, within another electric field, then you get a force acting on it, okay? And what's kind of cool like this is that force, that Q is supposed to be over there, is that force, they want to get pulled together, okay? And they want to get pulled together, there's potential energy there. And what that ends up doing is giving you something called volts. So the volts are joules per coulomb, the amount of energy per coulomb that you might actually have. And so a volt is a joule per coulomb, and it's the potential difference you have for charges from one place to the next. So let's say you got like a 12-volt battery. It's got, it's got that much potential, 12 volts, joules per coulomb, that it wants to get from one place to the other side. And so it wants to jump and move. So if you stuck a wrench in between the posts of a 12-volt battery in your car, which I've done several times by accident, holy crap, does it want to jump through. And I've had the wrench actually spark and turn red. And yeah, it's kind of scary. Put your tongue on a 9-volt battery. Okay, there's potential one to the next. Guess where those that potential goes through your tongue. Okay, it's doofy. Or you take cattle prod and you poke it in your brother's belly when you're in the alleyway when you're 9 years old and he screams like crazy. It's because those electrons traveled from one post to the other because there was potential there, and it went zipping through and made him lay on the floor and scream for mom. So the idea is that the potential, if you have potential for this to happen, now we can start the whole different process, okay? The whole different deal of making electricity work for us, okay? Now, what can happen is that you get electric fields on conductors. Okay, so we're going off a little bit. If we were in class, we'd be doing, I got this Van de Graaff generator back. And what happens is that you can have a device here like this Van de Graaff generator that can strip electrons off and put them somewhere else that, it takes them out of this right here. So the electrons are all gone. Well, now you have all positive charges left over. Positive, positive, positive. They hate each other, so they spread out all over the place. Okay, they spread out all over. And what ends up happening is you can get situations then if they're spreading out, well, if the object is perfectly circular, they're perfectly spread out, all over the place, like in this circle. But here, if we have one section that's kind of pointed together, well, in this section here, there's a bigger collection of charges than there is over here. Now, if that's the case, well, if lightning is up in the air, or potential for lightning is in the sky, and you have a massive collection of charges above you, well, if you are a pointed object on the ground, it's going to come to you first. So guess what you act as when you stand on a flat field and you stand there, all the charges are congregating on you in a tighter location than they are on the flat ground, and you're nothing but a lightning rod. And that field is really strong at the end of that, and the lightning then is attracted to that. That's what people used to put on buildings or lightning rods to try and attract the lightning, because the electric field lines right here are really strong, concentrated together, and the lightning will strike those first, kind of like the top of the Empire State Building. I think that's what it is. And on top of ships, they found out at one time that you've got air going past so rapidly fast, the electrons would the field lines were so strong on there that it would actually strip electrons off, and they go back to the ground state and they go off light. And so everybody always thought they were going to die, so they'd pray to Saint Almatius, the patron saint of sailing. I think that's who he is. And they'd survive. Well, obviously they survived. They told the story they lived because of Saint Elmo, and that's the idea of Saint Elmo's fire. And then a way to get rid of this is by something called grounding. So all these excess electrons built up somewhere, they're built up, and you can dissipate them when you touch somebody or something. You're actually grounding that thing out. You're letting electrons go through your body into the earth. Now, for example, when I fly my airplane, that darn thing will pick up so much electricity or driving your car. Watch videos on YouTube of people filling gas at a gas pump. Your car's tires on the ground, my airplane's wing through the air, it'll strip electrons. It'll be a huge electrical charge. So before I can put fuel in, I got to put this thing on right here. And that thing right there takes all the electrons and dissipates them into the earth. Now, just so you realize, the earth is the ultimate electron acceptor. They claim that there is not enough electricity on the planet unless you're, talking about something Star Wars-ish. There's nothing on the planet that will ever overcome the Earth's ability to accept charge. So all the extra lightning strikes, everything else, we could just keep dumping into the earth and it'll always take it. So grounding in our building is done where all the wiring in the building, they go through and there's a big copper rod somewhere in the ground. And the copper rod takes all the excess electrons out of our building so none of our electronics fry. You have it in your house also. Okay? All right. What that leads to is that we can actually harness this idea of storing charge. Okay? And one of the cool things here happened a long, long time ago is they invented or came up with this idea behind a Leyden jar. And it has to do with something called capacitance. It's a storing of charge. And what they did with this Leyden jar is you've got this glass jar, this black outer structure right here. This black outer structure. It's glass, okay? Does not conduct electricity. It's terrible at it. Electrons don't move. But you got a metal rod down through the middle, and they put aluminum foil on the outside, and they put aluminum foil on the inside. They're not touching, right? So they had a wire come down and touch the inside foil, and it's separated by glass. So guess what happened? They put a ton of electrons on the inside here. Well, the inside is completely filled with electrons. You just touch it by rubbing your feet on the floor and touch it with electrons. Well, the electrons are right here. Okay, they can't go to the other side, but what can they induce on the other side? They induce all the electrons in the outside to go into the earth if it's grounded. So what's left on the outside? Positive. Well, suddenly now we got a positive on the outside, negative on the inside. They can't touch each other. And so it actually stays like that unless you're dumb enough to take your finger, put it here, put your other finger here, and let the two touch. Guess what the positive on the outside, the negative on the inside are going to do? They're going to travel through your finger and give you a nice big old shock. That's a capacitor. How quick does it happen? Well, as fast as lightning. But you can actually harness these things. And a capacitor is a newer form of a Leyden jar, where it's the same basic idea, is you build up this charge, takes a little bit to get out the electrons in here, but it can release a ton of electricity instantly. And if it does it instantly, guess what? It could light up an entire room if you ran it through a light bulb, meaning that's how they will do. Old flash cameras would have capacitors in them that would fill up electricity and wham, let it go really quick. Would it be good to light your, if you're going to have your lights on in your house? No, because it goes instant and then it's gone. You got to fill it up. It means you would fill it up, let it go, fill it up, let it go, fill it up, let it go. And you'd have flash, flash, flash. Oh, hey, guess what that would work good for? The blinkers in your car. They fill up with electrons, release, fill up, release, fill up, release. And that's all it's doing is you're filling up capacitors and releasing them. Or you go down by the gym and down by the main office. You see the defibrillator on the wall, and you watch enough movies and shows where they put it on the person's chest and it says, charging, charging, charging. Guess what's filling up inside the defibrillator? A capacitor. It's filling up with all kinds of electrons on the inside. filling up, filling up, filling up. Stand back, stand back, stand back. And then I don't know if you push a button, I can't remember, that you have a pad on one side of your heart connected to the outside. You have a pad on the other side of your heart connected to the inside. And when the thing lets the current go, zap, the current flies from one paddle to the next through your heart and hopefully starts your heart again, all because they use a massive capacitor. Okay, so that's the idea behind capacitance. These things are modern capacitors, is what you'd find in, in electric motors or computers. They'll use these things to start things going, like an electric motor. It's big enough that it doesn't want to spin on its own, so it needs a little bit of a boost. And so what they do is, while you're running a motor, capacitors that are attached to the side, they fill up with electricity, so that when you shut it off, the electricity's stored, and then you want to go plug it back in, it lets go of the electricity and starts the motor for you. Okay. Other ones in your computers, sometimes they got to store them so you can start up programs the next time your computer's shut off. Never throw an unplugged computer in a bathtub with you, because there's capacitors in there that still give off a lot of electricity as they're stored, and they're all, you probably have seen these before inside of a computer or somewhere else. They're storing electricity. It's just paper wrapped around tin foil, same process, and you have like positive on one side, negative on the other, and you touch these two here, you get your shock. Okay. All right, so that's where we're going to stop for today with capacitance. And tomorrow we're going to set up circuits and talk about a lab that I'm going to have you guys do on very simple circuitry. All right, later.